I'm sure you're wondering, how could ln of 1 equaling 0 be a lie? Anything to the 0 power is surely 1, correct? Well, you are partly right. But what bothers me is the fact that the school system waits years to tell students the full, elegant truth about exponential functions. Not just log base e or e to the x, for example, which are both marvelous functions by themselves, but about all exponential functions in general. Now, this episode goes hand in hand with another one of my personal partisan views about a close friend of mine, C, the set of complex numbers, and my favorite mathematician, Carl Friedrich Gauss. But I'll speak more about that later. In this episode, I will show you a much wider view of mathematical truth. I hope you join me along the way. And as always, feel free to question or comment on my presentation. So in order to teach you why ln of 1 equals 0 isn't quite the complete truth, I need to introduce things called Maclaurin Series. So we have our let's say, in general, we've heard what a power series is. If we have just some sort of infinite sum. Now, more specifically, power series refers to some sort of sum that creates a polynomial, if I remember correctly. I'll get back to you on the formal definition, but power series is just our general term. More specifically, there's something called a Taylor series, which is very interesting. It serves as, think of it as a polynomial approximation. For some kind of function. For, let's say, for a more complicated function. Right, so we have a Taylor series, which is a kind of power series, and it's going to be a polynomial approximation. Let's say our more complicated function is y equals sine x. See, this isn't a polynomial in itself. In fact, it can be proven that this function of the sine function is really a transcendental function. In other words, it cannot be expressed as a finite sum that is a polynomial. Instead, it must be represented as an infinite sum. That's how you can think of it as. And if I remember correctly, we have the Taylor series formula is the sigma from n equals 1 to infinity, and it's going to be a fraction. Let me see if I can remember this, and I'll explain what this means in a moment. And really, for the first time, it helps to imagine this Taylor series in a more specific manner, and that is where it is. Well, we say it's centered at 0. It is a Maclaurin series. So the Maclaurin series approximation is basically a Taylor series that is, we say, centered at 0. Centered at x sub 0 equals 0. Right, so that's where our approximation is centered, and you can imagine that it simplifies this longer, more complicated formula, and basically we get sigma n equals 1 to infinity. So clearly it is an infinite sum, and we get f to the n of 0 times x to the n all over n factorial. And that is much simpler, as you can see. And by f to the n, by the way, I mean the nth derivative of f of x. So this is a notation you'll see a lot. It's very interesting. So we know f of x equals, well, I'll give an example. Suppose f of x equals 5x cubed minus 10x squared. Now we can say that f prime of x, earlier in this course we've learned to take derivatives, so we bring down the exponent, keep the coefficient as it is, and then decrement that exponent, make it 2. And then in this case we bring down the exponent again, keep the coefficient as it is, and then just multiply it by x to the 1. Simplifying that, we get 15x squared minus 20x. And that is our derivative. So f prime of x equals that. Now, we can say f double prime of x, find whatever that is. I'm sure that's probably 30x minus 20, yep. And we can keep going and going. Derivative of a derivative of a derivative. F prime 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 x really would be just 30. Anything onward, of course, will just be 0, since the derivative of a constant is just 0. But more importantly, the notation for this, if we had fourth derivative, instead of just putting 4 hash marks or like in Roman numerals, mathematicians say that we put this little 4 in parentheses, so f to the 4th, so to speak, of x equals 0, and that's just the notation. So we have the number in parentheses at the top, just to make it simpler when we're taking higher derivatives. Right, so this is becoming a longer video than I expected anyway. So Maclaurin Series is a Taylor series centered at 0. We'll see many examples of this. This is very interesting, and it's essential to proving a very short fundamental formula of mathematics, and I'm quite sure you will enjoy it, so please do stay tuned for that. I'm going to start by expanding more on this one function y equals sine x. So we know that y equals f of x equals sine x. Now, before we implement that formula for the polynomial approximation, we'll get back to that just for a second. Let's just focus on the derivatives of sine of x for now. I'm rather sure I've told you this before, but just please recall that the derivative of sine of x, and this is a very interesting property, is cosine of x. So, if you had forgotten that, yeah, here you go. That's what that is. So yeah, very interesting property. And then, well, continuing, if you were to take the second derivative, it would actually be, well, derivative cosine x, that's minus sine of x. So -1 times the sine of x. And these all can be proven. I'm just showing them to you now. If you were to graph them, you'd be able to identify pretty clearly that it was true, because if we were to take the cosine function, differentiate it, and find the points where cosine x has a slope of basically 0, we will find, it turns out that the function minus sine of x has values of 0 at those points. So we can deduce that minus sine of x is the derivative of cosine x. Now, from these two differentiation rules, from sine to cosine and from cosine back to sine, we can really deduce what the next n derivatives will be, actually. But I'll just... And if you'd like to make a guess of what the next derivatives will be, please feel free. It's simpler than you think, so I'll just unveil them to you right now. If you're... And so we get minus cosine x in this case. It's sort of like just a substitution. And then, of course, f to the fourth, so to speak, the fourth derivative of x. I shouldn't say f to the fourth, that's not quite right. It's not the right thing to say. Fourth derivative of sine. Really, it turns out we get, well, the negative of sine of x. So this is very interesting property of the cyclic nature of sine of x. So let me know if you have any questions, but that is a very good start to our proof here. So we'll continue this in a moment. I'll let you take this in for a couple minutes.